Thank you everyone for coming. I'm really excited to be able to host Emma Dodderman of Stanford to give a really interesting talk on backdoor-resistant U2F authentication tokens. I saw this talk at Real World Crypto in San Jose in January, and then she's also given it a few other times. I also caught the tail end of it at a FIDO Alliance plenary in Austin. It's really good. I'm so glad that you're here to hear about this amazing research. So without further ado, I'd like to welcome Emma Dodderman.
Thanks so much. Okay, so I'm going to be talking today about True2F, a system for backdoor-resistant authentication tokens. This work was done by myself, Henry Corrigan-Gibbs, David Mazieres, Dan Bonet, and Dom Rizzo, and was a collaboration between Stanford and Google. And our paper will be appearing this spring at IEEE Security and Privacy. So as you're probably all aware, hardware authentication tokens are a particularly effective form of second factor authentication token, with U2F tokens being especially popular. Since Google required just over a year ago that all its employees use these security keys, they haven't discovered a single instance of corporate credential theft, showing just how effective these tokens are. So the U2F protocol has two steps, and I'm just going to walk through a very simplified version of these two steps. So you first run registration when you're associating some token with your account, and authentication when then you want to log into that account. So simplified registration, you have some server. I'm just going to show it as github.com, send some identifier to the token. The token then generates some server-specific ECDSA key pair and sends the corresponding public key back to the server. It's important that this key pair is server-specific to provide unlinkability between sites. So you don't want two sites to be able to link a user through the fact that they're using the same token. So second step, authentication. The user's going to run this when they want to log into their account. So the server sends some identifier along with the challenge. The token is then going to get back the same server-specific secret key that it generated at registration and use that to sign the challenge. And it sends a signature then back to the server. So it's just a very high-level overview of U2F. Will be useful for understanding the rest of the talk. So in this way, U2F provides this really strong defense against phishing attacks as well as browser compromise. So in particular, if malware takes over your browser, it can't authenticate without interacting with the token. This is because the secret keys remain entirely on the token. No sort of useful cryptographic secrets are known by the browser. And so this provides a really strong defense against phishing as well as browser compromise. But what about vulnerabilities in the token itself? So U2F provides this strong defense against external adversaries, like a malicious browser or some phishing attacker, but the token itself might be untrustworthy. So there are two reasons a token might be untrustworthy. So it might be subject to these implementation bugs, or it might be vulnerable to supply chain tampering. So implementation bugs are a very real concern. So while you might remember, in 2017, secret key, and so they're actually able to sign the cryptographic challenge that is sent at authentication. So this is a pretty big problem, seriously undermines security that U2F is supposed to provide us. And so to address these two problems, implementation bugs as well as supply chain tampering, we propose True2F, which is the following enhancement to U2F. So we have three primary goals. The first is to augment U2F to provide a strong protection against faulty tokens. In particular, strongest link security between the token and the browser, where if either the token or the browser is honest, we can make certain security guarantees. Second, we want to do this in a way that's backwards compatible with existing U2F-relying parties. So we should be able to update both the token and the browser to run this new True2F protocol, but existing servers should be able to continue running U2F. This is important for real-world deployment because it's not very practical to actually ask all these servers to update. Finally, we want to do this in a way that's practical on commodity hardware tokens. So it should be both performant and only require a firmware update. So to achieve these three goals, we adopt the following two design principles. So first, we want both the browser and the token should contribute randomness to the protocol. This is important so the token can't use some bad source of randomness. Second, the browser should be able to verify all deterministic token operations. So the browser should essentially be able to check the token's behavior. So the U2F protocol has two steps, registration and authentication. And in True2F, we're going to add an additional third step, initialization, which will run after purchasing a token and before registering it with some site. So I'm going to start off by walking through initialization. And the idea here is that both the browser and the token should contribute randomness to the protocol. Okay, so in initialization, what we're going to do at a very high level is run some collaborative key generation protocol between the token and the browser, at the end of which the token holds some master secret key, and the browser holds the corresponding master public key. And we're going to leverage this master key pair in subsequent stages of the protocol. So you're wondering, well, why do we need to run this collaborative key generation protocol? Why can't just the token choose this master key pair, or just the browser? Well, if we had just the token choose it, the token could be using some bad source of randomness. So it might be using some bad random number generator, or it might be backdoored and choosing some secret key that's actually known to the adversary. Also, we don't want the browser to choose it entirely, because if the browser is ever compromised, the attacker could actually learn what the secret key was. And so instead, wait, okay,
Test.
Testing.
okay, cool. We're back. Thank you. Okay. So we don't want the token to choose all the randomness, and we don't want the browser to choose it either, because the secret should remain entirely in the token. So if the browser ever is taken over by some attacker, the browser should learn this master secret key. And this is why we want collaborative key generation. So just going to walk through the properties we want at a high level. So first, the token should be able to bias the master public key that's produced. This is important if the token has some bad source of randomness. Second, the browser should learn nothing about the master secret key. This is important for the cryptographic secrets to remain entirely on the token. So there's actually a protocol that already does this by Corrigan Gibbs et al. However, it's pretty slow on the small embedded device that we're using. And so we present a protocol that runs roughly 3 times faster on our hardware. So now I'm just going to walk through our collaborative key generation protocol. So we're just using some group G of prime order Q. Here is this P2P6 curve, and ECDSA key pairs having the form X and G to the X. So the browser starts off by choosing some values R and V, and then it sends a commitment of these to the token, so just the hash of R and V. The token is then going to select some value V prime, and then send back to the browser G to the V prime, which we'll just call big V prime. The browser now sets the master public key to be big V prime times G to the V. So the master public key is of the form G to the V plus V prime. The the browser then opens its commitment to the token and sends back V and R. The token is then able to check that the commitment received matches the hash of V and R. If this is the case, it sets the master secret key to be V plus V prime. So at the end of this protocol, the token is holding some master secret key of the form V plus V prime, and the browser is holding some master public key of the form G to the V plus V prime. So the first property we wanted is that the token shouldn't be able to bias the master public key. Here we get this because the token is choosing V prime, but it's the browser that's actually choosing V. And the token doesn't know the value V until after it's chosen the value V prime. The second property we wanted is that the browser learns nothing about this master secret key. And here we get this because the browser only knows V and G to the V prime. And from that, it can't learn what V plus V prime is. So that's initialization. I'm now going to move on to registration. And here, the idea is that all deterministic token operations should be verifiable by the browser. So just a reminder, in registration, the server sends some identifier to the token then generates some server-specific ECDSA key pair and sends the corresponding public key back to the server. So we can imagine some implementation bug that undermines the security of registration. So for example, the token might generate this key pair using some weak source of randomness. And so the server with this public key can actually determine the original secret key that's supposed to remain entirely on the token. We can also imagine some supply chain attack mounted against registration. So let's say if some attacker has backdoored your token and they're able to get you somehow to register at evil.com. So you go and you register at evil.com. The token can then generate some public key for evil.com that hides information about the secret key for another site that you've registered with, maybe github.com, for example. The token then sends this bad public key back to evil.com, and evil.com is actually able to extract information from this public key that it's received. So now, if evil.com manages to phish your password, it can authenticate as you with the secret key it obtained through this public key. So we'd like to sort of disallow both of these, and so to do that, we present verifiable identity families, or VIFs. And these essentially leverage the master key pair and allow us to generate these server-specific server-specific key pairs. So you might be wondering, well, why can't we just use the same collaborative key generation mechanism that we use in initialization? We're just creating these key pairs split between the token and the browser. Well, the problem with that, really, is that these tokens have a really limited amount of space. So we don't want to actually be storing all these secret keys on the token in a very small amount of flash. We want them to be as cheap as possible. And so to do that, we want to be able to derive these server-specific key pairs every time that we need them. And so these VIFs allow us to derive them in a deterministic and verifiable way from a single master key pair. So we don't need to store them. So we want the following properties from these VIFs. So first, the token should be able to produce the unique key pair for github.com. So it's important that this key pair is unique so the token can't leak information through which key pair that it chooses. Second, the token should be able to prove to the browser the public key is really the unique public key for that site. So the browser should, in essence, be able to check that the token is behaving correctly. Third, the server should be able to distinguish the public key it receives from a random ECDSA public key. This is important for maintaining unlinkability. So we should be able to tell that two public keys were generated by the same token. And finally, the browser should be able to forge a signature under the public key for github.com. If you could do that, that would sort of break the whole protocol. So now I'm just going to walk through a simple VIF construction. I'll sort of hint at what a more complex one that we present in the paper would look like. So here we're using some group G of prime order Q, again just the NIST P256 curve. And we're going to use the master secret key and master public key that we generated at initialization. So I'm just going to go ahead and rewrite this master secret key and master public key as X and G to the X, or just big X. We're then going to use this master key pair to generate this value K, which is just the hash of big X and is known to both the token and the browser. So now I'm just going to walk through the protocol. So the server sends some identifier to the token. The token is then going to use this identifier to calculate this value alpha, which is just the HMAC with the key K of the identifier from the server. The token then sets the server-specific secret key to be alpha times x, and the server-specific public key to be g to the alpha times x. The token then sends this public key back to the browser. The browser now wants to check, is this public key really the one unique public key for github.com? And so to do that, it can also calculate this value alpha with the HMAC of the key k of github.com, and then check if the public key that it received is equal to big X to the alpha. And so notice here it's able to check if the public key is formed correctly without actually being able to calculate the original secret key. If this is the case, it can send the public key back to the server. So the first property we wanted is that the token should be able to produce the unique key pair for github.com. And here we clearly get this because the value alpha is just the HMAC of the server identifier, which is unique per site. The second property we wanted is that the token should be able to prove to the browser that the public key it received is really the unique public key for that site. And here we get this because the browser can also calculate this value alpha and check that alpha is correctly incorporated into the public key. So it can calculate this value big X to the alpha and check that that equals the public key. Third, we don't want the server to be able to distinguish the public key it receives from some random ECDSA public key. And here we get this because the server can't actually calculate this value alpha because it doesn't have the key k. That's only known to the browser and the token. If it knew this value alpha, it could actually link these keys, right? It could just divide up alpha and see that they come from the same big X. But it doesn't know this value alpha, so we're fine there. However, you might not want the browser to actually be able to link these keys. And so in our paper, we actually present a more complex construction of these VIFs that actually makes these keys appear unlinkable from the point of view of the browser. And we do that using verifiable random functions. So the token is essentially able to calculate this value alpha, give it to the browser, and prove to the browser that this is in fact the correct value for alpha without the browser being able to calculate this value of alpha on its own. And if you're curious exactly what that construction looks like, happy to chat after. You can also check out the paper. But the final property we want is that the browser shouldn't be able to forge a signature under the public key it receives. And you can check out the paper for a full proof on that if you're curious. Yeah?
What is a hash of the big X used for?
That's used as the key for the HMAC. Just the HMAC with the key K. Yeah. Okay, so that's registration. I'm now going to move on to talking about authentication. And here, the idea is that both the browser and the token should contribute randomness to the protocol. So just as a reminder, in authentication, server sends some identifier and a challenge to the token. The token then signs this challenge using the server-specific secret key it generated at registration. So just some quick background on ECDSA signatures, sort of everything you need for the talk. These ECDSA signatures are randomized in two ways. So first, through some signing nonce that should only be known by the signer. And second, these signatures are malleable, meaning that if I give you any one valid signature, you're able to calculate the second valid signature without knowing any additional information. So based on that, we can now imagine some implementation bugs that undermine the security of authentication. So for example, the token might choose a signing nonce with some weak source of randomness. And actually, it's been shown that if you have a lot of these signatures where the signing nonces have been generated using weak randomness, it's actually possible to rederive the original secret key used in signing. And so if the token has some weak source of randomness, this is very problematic for authentication. Supply chain tampering can also undermine authentication. So for example, the token might try to hide the secret key for another site in the signature. So it could do this in one of two ways. So it could choose some signing nonce that leaks information about the secret key, right? Since the signer, the token, gets to choose this randomly on its own. It could also do that. It could also leak this information very slowly over time through which of the two valid signatures it chooses to send. So exfiltrating 1 bit per authentication. So in essence, the signature is acting as a subliminal channel here. So this wouldn't be a problem if we could use some unique signature scheme like BLS or RSA full domain hash. But here we're limited to ECDSA because we need to maintain backwards compatibility with existing relying parties. So these servers are expecting ECDSA signatures. We have to give them ECDSA signatures, even though there are all these randomness problems here. And so to solve this problem, we present this primitive we call Firewalled ECDSA signatures. inspired by recent work on cryptographic reverse firewalls. And so we want the following properties for these signatures. So first, the token should be able to exfiltrate any bits of information in the signature. And these properties are based on previous work on subliminal-free and subversion-resistant signature schemes. Second, the browser should learn nothing except for a valid signature. We formalize this notion of zero knowledge more fully in the paper, but essentially we don't want to be trusting the browser any more than we do in traditional U2F. So now I'm just going to slowly build up the idea of our construction for firewalled ECDSA signatures, hopefully without getting into a lot of the nitty-gritty of ECDSA signatures. Although again, if you're curious for that, you can check out the paper. So here, this is just regular U2F authentication. So the token receives some challenge, just signs it using its secret key, sends it back to the server. So ECDSA actually has this cool property that if the signer has R and the signer signs using this nonce R, anyone else with GDR can actually verify that R was used in the original signature. And so what we would ideally like is we would like the token to hold some signing nonce R and the browser to hold GDR, so that the browser can verify that the signing nonce was in fact incorporated in the signature. So then the question becomes, well, how do we get this R and GDR split between the token? And we need a new R for every signature. And so to do that, we use the same collaborative key generation mechanism that we used in initialization. So that gives us our R at the token and GDR at the browser. And so if the token signs using R, the browser can use GDR to verify that the signing nonce was incorporated correctly. So this solves the signing nonce problem. We still have this problem of malleability. So the token can send any one of two valid signatures, and so the token could leak one bit of information per signature through this. And so we solve this problem by having the browser just randomly choose one of the two valid signatures to send back to the server each time. So the first property that we wanted is that the token should be able to exfiltrate any bits of information in the signature. And here we get this because we're taking care of both sources of randomness. So for the signing nonce, we're collaboratively generating that between the token and the browser is able to check that the token is using the correct source of randomness in the signing nonce. We also are re-randomizing the signature, which takes care of the malleability problem. Second, the browser should learn nothing except for a valid signature. And here we get this property because the secret key and signing nonce remain entirely on the token. So the browser only knows GDR and the public key, and so we're not trusting it any more than we did in original U2F. So I've now gone through all three steps of the protocol. So there's some other contributions that I'm not going to talk about today, but you can check out our paper if you have questions about them or are curious, including a flash-optimized data structure for storing U2F authentication counters and cryptographic optimizations tailored specifically to the token hardware. So I just want to touch on one implementation point. So U2F doesn't require the browser to store any state about individual tokens. However, you might have noticed that True2F actually requires the browser to keep track of some state, in particular this master public key corresponding to each token. And so there's sort of several ways you might go about doing this. Just sort of want to briefly touch on those. So one option is that the token could give the master public key to the browser. So every time you plug in your token, it says, here's my master public key. While this provides some protection against implementation bugs, since the token gives the correct master public key, the browser can then audit it. This isn't very satisfying because if you have some malicious token, it can just give the wrong master public key. So maybe that's probably not the best solution. Another approach would be to actually sync the master public key across browser instances, the same way that you sync your bookmarks. This would provide you with sort of more, this would make it harder for the token to then cheat because all these browser instances then know the master public key. So we also implemented True2F on Google hardware. So on your left, you can see a Google development board running True2F. This is where we got the evaluation numbers from that I'm about to show you. And on your right, you can see Google production USB token with the same hardware specs. So not currently running True2F, but capable of running it in the future. So when we first started implementing True2F, we knew that there would be some overhead to using True2F in comparison to original U2F. So we're adding this collaborative key generation and all these checks, and so we wanted to reduce this overhead as much as possible. So here we're just looking at the authentication protocol latency. It's just the time doing the crypto in the browser and the token. And we can see without any optimizations, True2F is pretty expensive in comparison to original U2F. So 446 milliseconds in comparison to 23 milliseconds. However, we can add a variety of optimizations to actually reduce the latency to about 57 milliseconds in comparison to 23 milliseconds. So True2F is only about 2.5 times slower than original U2F. We're focusing on authentication here because it's the common case, but the story for registration is pretty similar, about a 2 to 2.5x overhead for using True2F as opposed to U2F. So this is the actual protocol latency, but we were also curious what latency the actual end user experiences. So here we're measuring the time from when the browser is able, actually receives a request to when the browser is actually able to respond. We found that a lot of time is actually being spent in browser middleware, as opposed to actually being spent doing crypto on the browser or the token. And so the end user is not actually experiencing this 2.5x overhead. They're only experiencing a 12 to 16% slowdown, only an additional 20 to 30 milliseconds of delay. It's also important to keep in mind here that normally these tokens require you to actually tap them to authenticate, and so that would mask a lot of this latency as well. For these tasks to be instrumented, the token do not require that. So in conclusion, True2F shows that we don't need to settle for untrustworthy hardware. It augments U2F to provide a strong protection against backdoor tokens, in particular, strongest link security between the token and the browser. It does this in a way that's backwards compatible with existing U2F servers, requiring only changes to both the token and the browser, but not updates to the server. It's also practical to deploy in that it's performant on commodity hardware tokens with only a firmware update. So U2F allows us to defend against phishing attacks as well as browser compromise, but True2F allows us to go one step further and make these security guarantees even with potentially untrustworthy hardware. So our paper will be appearing in Oakland this spring. You can check it out if you're curious, and I'll take any questions, and thank you.
How prevalent were these instances of backdoor tokens?
So his question was, how prevalent are these instances of backdoor tokens? Well, we don't have any concrete examples of these U2F tokens being backdoored, and currently there are a relatively small number of manufacturers, and there has been no concrete evidence. However, you could imagine these types of attacks and this type of attack potentially coming out in the future. Like there was this big Supermicro scare this fall. We can imagine that type of thing being a problem, and even if we don't have concrete evidence that this has happened with these security keys, this is something we should be worried about potentially happening to U2F or something similar in the future.
I was curious on your specific selection of elliptic curve. Was that based on hardware constraints, or if you could tell?
Yeah, so that's just what the original designers of U2F chose. And so part of using that elliptic curve choice, part of using P226 was just the fact that that's what U2F was already using.
Thank you. Hopefully this isn't extremely obvious, but so you kept showing this token to be paired with like a GitHub account. So, I mean, what if you lose the token, it breaks or whatever, you have to have some other way to get back into your GitHub. So in theory, couldn't you bypass it somehow still?
Yeah, so that's actually a great question. So there's actually a lot of thought right now going into how you actually do backup with these tokens. So currently, if you lose your token, you can't really get back into your account unless you actually call customer support. Different sites might have some way of getting around this. But basically, if you lose your token and the site is asking you to provide, your token needs to sign this challenge, there's not a way in U2F to get around that. And so people are looking for nice ways to do this, and there's not a great one yet.
Okay, well, at first you said you could call customer support. Would they be, so you're saying they wouldn't be able to do anything, so you'd just be locked out of your account then?
Well, they'd be able to go in and manually remove that key and sort of manually let you back into your account. I've heard stories from people who've tried this. I've heard stories from people who are both successful and unsuccessful doing this, and I think that's a concern with the adoption of these tokens, and one of the reasons people are a little bit more reticent to use them is if you lose them, if you lose one, there's not a great way of getting back into your account unless you register 2 keys with every site, and then you can have a backup key. But that's a little more tedious.
Or you are allowed to register multiple keys with a given account?
So the question was, you're allowed to register multiple keys with an account, and yes.
Oh, okay.
When you were showing using your key across multiple browsers and devices, did you guys also explore tying the browser and the website to a particular key on your device? So in that case, you register multiple keys for each device that you're on?
That would be one way of doing it. I think there are companies currently looking at even like building these keys into your laptop, and so we might be looking at a world in which that's how authentication is done. Maybe, I don't know. I think a lot of people have different views on how that will move forward.
I don't know if this is the right question to ask, but what's your perspective on the tokens that you can build on I don't know, on the cell phones and so on, like apps,
Yeah. So the reason that these small embedded devices are really attractive is that they're a really small attack surface. So it's a lot harder to get malware onto your small U2F token than it is to get it onto your phone, for example. And so the attraction is you have these cryptographic keys that remain on this small embedded device that the attacker is likely not able to compromise. And so our work was looking at, well, what if you get a token that is compromised? But that is the appeal of these security keys.
Yeah, I'm curious what the shortcomings are of schemes like deterministic ECDSA that led to the construction of the the Firewalled ECDSA approach.
The shortcomings.
Like there are certain deterministic ECDSA schemes, and I'm thinking maybe it's just because they're unverifiable by the browser. But I'm wondering what led you to construct the Firewalled ECDSA scheme.
Yeah. Okay, good question. Yeah, so we wanted to, so we don't want to trust the browser at all. And so we don't want to split some key across the token and the browser. And also, so there are some more general schemes, more general supplemental free subversion resistant schemes. However, they're actually pretty slow to implement in practice. Our token's crypto is very slow. I don't know if you these numbers here, a signature takes up almost all the time in this U2F, so it's almost about 20 milliseconds. So you don't want to add a lot of these sort of more general purpose things that are great, in theory, but maybe aren't that fast on this, sort of small ARM processor. And so performance actually drove a lot of these decisions, as well as where we actually want to place our trust, and the browser needing to be able to check all the randomness.
You mentioned one constraint being the memory that a token could store. Are there any significant differences between True2F versus U2F?
So we were using the same hardware. So the hardware that we were using was designed at Google for these U2F tokens, and so we were just using the same hardware. And part of the idea behind the U2F spec is that you shouldn't actually need to store these secret keys in the token. And so we wanted to have our protocol not, keep this assumption that you could not require the token to store these secret keys. And so that was sort of a requirement because the U2F protocol had that in there.
You mentioned that you're using the same tokens as the U2F, so obviously you're reprogramming those. What do you have in place to stop, say, a malicious browser from going in and reprogramming a good True2F token or U2F token to a malicious one?
Yeah, so that's a good question. So that's why it was actually so difficult to do this work. So normally if you have a UV key, you actually can't program it yourself. You need a secret signing key to load firmware onto the token, and a lot of these, and they're all very obviously locked, so you can't mount that kind of attack. And so the hardware that I was working with, I needed to be employed by Google to have access to, and I had to get special signing keys. So that's how I got software or firmware on there.
In a world, thank you.
In a world in which everyone is using True2F, what would you guess the next major attack vector would be?
That's a fantastic question. That's a really great question. I don't have a great answer to that. I think that there are so many hurdles to getting the whole world to use second factor, let alone security keys, let alone True2F. I'm having trouble imagining what that world would look like right now. However, I'm happy to chat more afterwards. I'm really sorry I don't have a great answer right now.
Forgive me if this is kind of a dumb question, because I'm new to UTF in general. But one of the things you pointed out in your presentation is that it seems like it's reliant on the browser to do a lot of this calculation. And I live in a world where my users are device agnostic, and they're not using, I mean, if someone's computer breaks, I'm giving them a spare computer. That machine has probably no information about them until they start logging into all their online accounts. So, you mentioned, potentially syncing the master password key through browsers, but at the point that if an account got compromised, you're now syncing that, and that seems like it's introducing an element of risk. And so I'm curious, to hear your thoughts on, how do you make this device agnostic, where it's not reliant on a specific machine, and then also protecting it when you're trying to store it, like that?
Yeah. So that's actually a good question. So I think you're sort of getting at this concern of, well, let's say I'm using Chrome to now sync my master public key, but that's actually an account, and I'm logging into my browser. So, well, what if my Chrome account is compromised? This isn't a great situation. I think that we're seeing something similar already with these password managers, where your one password manager is sort of in charge of managing all your accounts, and if someone gets in your password manager, that's not great. And while that's maybe not a great situation either, I think that there's at least a story there, and for a reason you might want to move into, it might be reasonable to say, well, I don't think that the attacker is going to be able to get into my Google account, but maybe the attacker will be able to get into that one random account that I made for that, one thing that I needed to do that one time, and I forgot I even had an account there. So I think, but that definitely is a concern. I think that sort of relies on the idea that it's harder to break into the account that's doing the syncing than some of the other accounts.
So we're all using, or we all, U2F instead of the 6-digit passcodes to avoid being phished and so on. But if I'm actually using multiple devices and I want it to sync between browsers, do I necessarily need to have a non-True2F second factor method in order to sign into the other browser the first time? Otherwise, do two-factor into the browser to sync it, I would need True2F, which only works on my first browser.
So that's actually a good question. You're not the first person to have asked this question.
If this was the RWC question, I'm very sorry.
This is not the RWC question, but thank you. That's a reasonable concern, and I think that you could maybe have like some sort of other mechanism for getting it. You just sort of essentially need some way to bootstrap this, and so I don't have like a super in-depth answer for how exactly this sort of process of syncing would work, but that would definitely be something that would need to be addressed. And maybe for logging into your browser, you would have some other way of logging in. Maybe you would have I don't have a great answer for that right now. I think I did. I'm happy to chat about this more after if you're curious.
I was wondering if you could go into a little more detail about, assuming you could break compatibility with U2F, what are the changes that you would make to harden the security of the protocol?
Yeah, great question. So I think that, first off, we probably would not be using ECDSA, so what we had to do was like a little bit hacky. And I think that there would ideally be hopefully there would be like some better support for sort of handling this sort of syncing of state and making initialization easier. I think that there are ways, because of, so in the original U2F protocol, you have to keep track of this key handle. And so the token generates this key handle at registration, and then the token then needs this key handle for subsequent authentications to sort of remember the key that it had before. And so there might be a way where you could actually sort of unify authentication and registration into one step, because it can just derive this key every time and doesn't need to know whether it gave the server that key beforehand. I think that I've talked to several people, and that might sort of make some parts of the protocol easier for developers to work with. So that could be an interesting direction. I think if you weren't tied to the exact protocol format, you could maybe even do some other cooler, like fun cryptographic things as well. Definitely get better performance. You just wouldn't, you wouldn't be tied to this, having to keep it, the byte compatibility, which would be nice.
We have one question remotely. So if you could go back to the slide that says exfiltration resistance. Yes. So the question is, what is G?
So G is just a generator for the group.
Thank you.
Yeah, just kind of one naive question. You brought up the fact that, to do this, all of a sudden, the execution time was down, was in the 500 millisecond. In the world of the internet, that's not all that long. I mean, really, was that really that big a concern? I mean, gosh, you probably spend the browser spends more time trying to like resolve the domain name or whatever than it would to execute this. It's,
Yeah, so I suppose, so on the one hand, it's not that bad, but of course, as developers, I think we always want to like do better, and I think, anytime you can make, you can sort of decrease latency for the user is a win. And a lot of the optimizations that we make, are sort of, cryptographic and sort of finding these, cool tricks to speed things up. And I think that sort of, making the experience of, security faster is always better. Because, if the user seems a little slower to them, maybe they're less likely to use it. So.
It just seems like in the grand scheme of things, that's like nothing compared to everything else that's required to sign into the site.
Yes, I suppose just like adding to that layer, that right, you have this sort of huge stack of, you should have this like long list of, things that need to be done before you can, load the web page or authenticate, and you want to make sort of each sliver as small as possible. And it's easier to convince people to use your thing if that sliver is as small as possible. If you add up all the slivers, and that suddenly gets very big, it's a problem.
All right. Give Emma one more round of applause. Yeah, so just again, I want to thank Emma for coming out and giving this really great Duo Tech talk on True2F. I think it's really like promising to me personally that we don't just accept the strong security protocols that we have today. Like there are people in the world that are like out there trying to make everything better. So just once again, thank you. So, cool.